masterthesis presentation about an open-source adaptive event-based ADC for biosignal acquisition in 130 nanometer CMOS. So my thesis is basically structured like you would design the flow of an ASIC. So at the beginning I did a lot of literature research, which is for event-based ADCs really important, as I will show you in the next couple of slides. Then I built a demonstrator to prove the functionality, and in the end I wanted to build my own ASIC design, so my transistor level design. So I made a system level design, designed the transistor level circuits, made the digital layout, mixed signal simulation, and the red boxes is the outlook, what will hopefully be tackled in the future. So, what are event-based ADCs? I think it's good to compare them with Nyquist ADCs because hopefully everyone is familiar with them. Nyquist ADCs sample the input at the fixed sample rate and therefore generate uniform samples. And they quantize and encode the voltage values, so we get amplitude quantization. On the other hand, event-based ADCs only produce samples when the input exceeds a predefined threshold, in this case denoted with theta. So we get non-uniform sample pulses, also called spikes. And here we now have, we measure the time between these spikes and de-encode them, so we get time quantization here. And where is this useful? For example, for sparse signals. What are sparse signals? For example, a ECG signal. Sparse signals are signals where you have a time interval with less amplitude variation and a short time interval with high amplitude variation. And here event-based ADCs decrease the number of samples, the storage resources, computational effort, and the power consumption. In the time domain it looks like this. For Nyquist ADCs we see the amplitude error and the uniform samples. And for event-based ADCs, we see that we have no amplitude error, but we have non-uniform samples in time. And again, here the threshold theta. How can we implement event-based ADCs? There are basically two topologies. One is the floating window architecture. Here, when the input signal rises above the upper threshold voltage, the output of the comparator is a logic 1, and that both dark voltages are shifted by the threshold theta. So the window is floating with the input signal, hence the name. Another interesting architecture is the fixed window architecture. Here the thresholds are fixed, but the signal is always wrapped into this window by subtracting the current dark voltage V dark. And this has the advantage that the comparators don't need to have input rail to rail, so they can be optimized at the specific voltage range. So we also have aliasing here. For a Nyquist ADC, we have the well-known Shannon limit. For event-based ADC, on the other hand, we have something called an aliasing effect, and this is what we can compare with a slew rate. For example, when the input slope is higher than the maximum slew rate of the event-based ADC, we cannot follow the thresholds and hence cannot sample the signal anymore. The slew rate is mainly defined by the threshold and the loop delay. And the loop delay consists of the propagation delay of the comparator, the processing time of the digital core, and the setting time of the DAC. And if we, for example, plug in the slew rate for a sine wave, we can actually derive the maximum frequency, the maximum input frequency for fixed thresholds for a sine wave input. And we see that T loop and the DAC resolution F are the main parameters to tweak here. And we also have an SQNR. Again, for Nyquist ADCs, we can derive the well-known formula for a full-scale amplitude sine wave and with uniformly distributed amplitude quantization. And this depends on the ADC resolution N. On the other hand, for event-based ADCs, we don't depend on the feedback DAC resolution F, but on the clock resolution of the digital core, or how we encode the spikes. and the input signal's frequency. And this is, can be simplified with the oversampling or resolution factor R. And what is the main takeaway here? So we can now build event-based ADCs that achieve a higher SQ&R compared to an n-bit n-Nyquist ADC with lower duct resolution, so f is smaller than n. For example, to have example with values, if we have an 8 MHz clock and a 500 Hz input signal, then we get around 70 dB. This would be around 12-bit effective for an Nyquist ADC, but we can achieve this with a 5-bit feedback duct. And this also reduces the noise of the total system. So the design requirements are much more relaxed. And then we can build the analog front end in two ways. The first way is continuous time. So we have a continuous time comparator, a continuous time DAC, or an asynchronous or clockless digital core. So we can here minimize the clock uncertainty and also the loop delay. Ideally, these ADCs don't have an amplitude quantization, no time quantization, and no aliasing, which is really incredible. But they're limited by the high power consumption, because they always consume power, and of course the non-idealities of the analog front end itself. So, a promising alternative are discrete time systems, where the analog front end is always triggered periodically or adaptively depending on the input signal. This reduces the power consumption, but again, on the other hand, we introduce clock uncertainty here, and we limit the slew rate to the trigger period, which must obviously be higher than the loop delay. And then there is adaptive threshold-based sampling. This is mainly developed in the Institute of Signal Processing. And with this we can adapt the threshold depending on the input signal. We therefore can reduce the number of samples, and we can increase the maximum slew rate. And without going into any mathematical details, we can calculate the Wells discrepancy for a defined time window. And if this discrepancy is larger than a certain value, we double theta, and if it's lower than a certain value, then we half theta. And just to have some state of the art right now, a lot of people are doing floating window compared with single-ended, or fixed window with fully differential outputs. And there is only one event-based ADC with a discrete time analog front end. So we want to do now a combination of everything. So a fixed window, fully differential, adaptive thresholds, and a discrete time event-based ADC. But first we want to prove the functionality of event-based ADCs in general with a PCB level demonstrator. This is implemented with a single-ended architecture and floating window and with commercial ICs. And with 8-bit feedback DAC, but we can set it in the digital core, to example 5-bit also. The generated spikes are then transmitted to a notebook via a UART to USB converter, and then are reconstructed in MATLAB or Python. This here is the analog front end PCB, and the whole demonstrator is this. So we have the analog front end PCB, and here we have the FPGA board, and optionally you can also transmit data with Ethernet. And for an ECG signal, this looks like this for the threshold-based sampling case, so with fixed thresholds. We see that the QRS complex is well sampled, but here in the sparse time domain we have less samples. So for adaptive threshold-based sampling, we now have two parameters in the digital core we can tweak to increase or decrease the samples. For example, for a 5 millisecond time window, we get 330 samples. For a 60 milliseconds time window, we get 165 samples. So we can reduce the samples in sparse time intervals. And if we want to further decrease the samples, for example, during the QRS complex, we can increase the maximum theta and now obtain 118 samples. And the cool thing now is we don't even lose SNDR in the frequency domain. So here we have the reconstructed signal, spline interpolated, FFT transformed, and then we calculated the SNDR. For an 8-bit threshold-based sampling and an adaptive threshold-based sampling, we nearly have the same SNDR. But the main advantage now with adaptive threshold-based sampling is, for each period we only have 13 samples, because we can adaptively change. On the other hand, for an 8-bit threshold-based sampling, for full scale we have 500 samples. So the compression ratio, the maximum compression ratio here is 17, which is a really nice advantage of adaptive threshold-based sampling. And finally, we come to the ASIC design. Now we see the fully differential fixed window discrete time event-based ADC with adaptive thresholds. For that, we need discrete time comparators, in this case dynamically biased ones, so we further reduce the power consumption. I implemented a capacitive DAC with 2 fully differential outputs, and to obtain the common mode voltage, I implemented bufferless charge pump, and the input is amplified with a biosignal amplifier, a low power, low noise one. And the amplifier core consists of a telescopic input stage and a push-pull output stage, which are both biased by a beta multiplier reference. And the common mode output voltage is set by switch capacitor common mode feedbacks. C1 is programmable, and we can adjust the gain of the amplifier. And the lower cutoff frequency is programmable from, can be set, for example, to 0.3 Hz, and is a 5-stage shunt capacitor, switch capacitor resistor, and all those switch capacitor resistor need a non-overlapping clock, and this is generated in the digital core and is synthesized. And the functionality is shown here, so we can see the behavior of fixed window architecture. So in gray and in green we have the output of the DAC. And the comparator output is shown, for the upper comparator is shown in red. So if the signal increases, the upper comparator is 1. If the signal decreases, it is 0. And for the lower DAC, it is the other way around. So if the sine wave decreases, the lower comparator is 1. And this 0-1 encoding is now put in the digital core, and we can get the spikes according to this information, and then can reconstruct it on the notebook later on. So, what have I achieved during my master thesis? I have found important theoretical findings. I proved the concept with a PCB level demonstrator. I developed a new architecture which combines the most important advantages, and I did a transistor level design of all the blocks you have seen before in the block diagram. Of course, we have digital layout, we don't have an analog layout yet, so I have to do this in the future. Of course, post-layout simulation with parasitic extraction, then the tape-out, and finally the chip should be verified with measurements, and hopefully someday we have a working chip which is producing spikes, which then can be used the Institute for Signal Processing for further investigation. Thank you very much. If you have any questions, please do not hesitate.